traditional for us to be supporting. Certainly, Python is a huge one, and R. We're also seeing some interest in Spark, and then we get into machine learning sorts of software such as TensorFlow, CafeNet, other things like that. Now we're also adding on data technologies such as Spark, or such as Shifter, and some possibility of OpenStack, but that's probably more of a separate deployment for us. I'm curious, how many of you are supporting Python on your HPC system today? Pretty much, well, not everybody, half the room. How many of you are having trouble supporting Python on your system today? But quite a few. I mean, it's not a trivial thing to support. There's a number of different ways to do it. Easy Build, for one, is one you can deploy current versions of Python and a number of packages. We happen to have a guy on staff who has taken it upon himself to support every package under the sun. So we have something in the order of 400 different Python packages that are built and supported on Python. The only problem I have with that is I think he's the one that knows how to do it. So if he leaves, we're in trouble. I'm guessing that some of you have similar sorts of situations where it's a little too tied to one person in terms of support, which can make you a little nervous when something personnel changes happen.
You don't use virtualing?
Sorry?
You don't use virtualing and let the users break their head about installing their packages?
That would be a traditional way to do it, yes. This particular guy is a little bit crazy. Whenever somebody writes in, he pretty much goes and installs it for them. It's a general package. So in a way, it's very good customer service, you could say, but it's also setting a bad example in other ways, right? So we really do have 400 packages there, and I'm pretty sure that even he doesn't have any understanding of most of those packages and how they operate. So we get them installed, that doesn't mean we know how to operate them or support them. So that's a little bit of a problem as well. And we look forward, we're also looking to add extra services such as tiered storage services. Even on Blue Water, as I think I mentioned yesterday, we're working on a method to have policy-driven file migration between our disk subsystem and our tape subsystem. That will basically change how we manage our large scratch file system from being a traditional scratch file system where users have a quota and a purge policy where they have to take explicit discrete steps to make sure that data doesn't get purged off of it if they need, to one where it would be a quote managed file system. In the managed file system, there's a set of policies. You still have quotas, but you have a set of policies that when data ages to a certain point, it gets copied onto the slower storage, in our case tapes. And at some later time, when the level of usage of the file system is managed, typically you release the storage. This is dual resident on disk and tape. You release that storage from the higher speed disk subsystem. When you release it, then basically the metadata space covers both. So that when you release it, you still see it if you do an LS on your file system. But if you try to open the file, it will issue a retrieval command and will block until the file is actually brought in from the back of the storage. So that's useful. It helps, reduces some level of effort on the users. On the other hand, they do have to take steps to make sure that they stage that data properly on the disk before they run a compute job. You certainly don't want the compute job to be the one that fires up the parallel application 1,000 nodes, tries to do an open on a file, and then waits an hour while it retrieves the data from tape. That would obviously be bad for overall system utilization and science throughput. So it trades one complication or explicit data management on the hands of by the user for a different one where they have to make sure that the data is where they want it to be. I should also mention that one of the things I'm not going to talk about a lot here, at least not in the slide deck, is long-term data storage. I'll talk a little bit about that in a minute. And what people do with data that's no longer active but needs to be kept long-term or made available to other science teams outside of the local system. So I just threw my Blue Water slide to remind people what it is. So as I mentioned, it's a fairly traditional system. So I didn't take one of the numbers in the slide, but from the data point of view, the key aspects are it's large memory, fast file system, 1 terabyte per second, and reasonably large spinning disk store, 46 petabytes. Though if you really consider this amount of storage compared to the size of the system, it's actually not that large. A lot of smaller scale systems would have a much higher relative amount of storage. So that means that we do have to manage this space fairly carefully so that users don't fill it and make it unusable by the people that actively running jobs. So to make up for that somewhat relative lack of space, that's why we have the large tape subsystem. The idea of that is if you have a run that you need to do later analysis on, you're not actively doing things, you move the data off of here onto the tape subsystem. The tape subsystem is obviously much slower. It's relatively good as a tape subsystem goes, but it's still much slower than the high-speed disk subsystem. But this can handle petabytes of storage for each science team and grow pretty much as needed. We originally spec'd this out to be even larger than 200 petabytes, but we found as we got into operations, the users actually weren't using it as much as we first expected. So we currently have about 30 petabytes of user data in the system, which is quite a bit lower growth rate than we originally anticipated. So we don't anticipate actually getting anywhere near 200 petabytes of actual usage by the end of Blue Water's lifetime. But we still do have science teams, multiple science teams that have more than a petabyte or more than 2 petabytes even of data that they're storing in there. Usually those are the usual suspects in terms of applications. So the folks that are doing things like climate or other sorts of time-dependent long-term runs that need to store large amounts of data to do a later analysis. Except for put the slide in there for the overall piece of this too. So other pieces of our data management strategy include these data mover nodes. I guess I didn't put a slide explicitly on this, but just talk about that a little bit. The way we do data movement between our Lustre file system and the tape subsystem is actually primarily through Globus Online, or Globus. How many folks here use Globus? Not very many, actually. Okay, so Globus is a project that basically provides a nice, reasonably nice web interface to set up your data movement for basically grid FTP. So the back end is grid FTP. Our things here that are labeled import-export nodes, and we have 25 of these, and we have 50 of these HPSF data mover nodes. Those are all like grid FTP servers. And when you set up a Globus transfer, it will parallelize that transfer across all available nodes as needed to maximize the data movement. So with grid FTP, even on a single server, it's going to multi-thread that transfer to parallelize it as much as possible. So you're not worried so much about the performance of an individual thread and transfer to maximize. You're just saturating the bandwidth by throwing lots of different transfer threads at it. And that works pretty well. One of the problems that we have with Globus is that it actually makes things too easy for users to do the wrong thing. It's very easy for a user to come into Globus and say, hey, this is my results directory. Just copy the whole darn thing over as is to our tape subsystem. Sounds good, works, but if they have 1 million files in that directory, when they come back to retrieve them later, you actually can't index them in the GUI interface of Globus and pull them back over. So it unfortunately makes it too easy to drop a gazillion files in a place on a tape subsystem. The tape subsystem is really not capable of doing that indexing as well as the file system is. So we're still working with Globus on ways to make that more effective. And even on the file system, the Globus interface is not really set up to be able to index it directly with large file count. It really wants to deal, because you're dealing with a web interface with just a regular list. So it's obviously if you get a million files in a directory, that's a problem. It just doesn't have the methods to handle that. So that's one of our problems with it. Of course, Globus is a sort of a paid service. If you run a large service like we do, we actually have to pay into it to be able to support users from multiple sites and multiple institutions on it. But overall, if that works out, for us anyway, it makes a lot of sense. We are also back in this authentication to our authentication. So we do RSA two-factor authentication throughout. they can do a certificate-based authenticated with the two-factor token. So we basically get a certificate that lasts for about a week, so less Globus transfers go on in the background. The other benefit of Globus and Grid FTP in general is it manages the retries. So if you do have a large number of files, one of the biggest problems people have, of course, is making sure the data is actually transferred as it's supposed to be. And Globus and Grid FTP manage that so that basically once you transfer this data over, if the endpoint goes down or something happens in the transfer, it'll just keep retrying that at least for a number of days and keep making progress. And so it removes the user from having to do a lot of babysitting of the transfers to make sure the data is transferred across. So in general, we think it's a reasonable solution. It's not ideal. There are problems with Globus, but at least at the moment, it's one of the better solutions out there. Although it does require some fees, at least in the higher tiers of service. I think for you can run a personal server, you can actually download for free the server and run it to your laptop, Connect or something like that. It's called, and run it directly on your laptop or even on a server. Just a matter of how many users you want to have and whether you can back end the authentication or not, that sort of thing. All right. Well, first I'm going to jump into long-term data storage. We had a couple of comments yesterday about our long-term data storage strategy, which kind of reminded me of this particular sort of strategy, which some of us do still use, but users tend to not like that if they do want the data back eventually. So, it is a problem though. One of the problems we have with Blue Waters is, prior to Blue Waters, National Science Foundation in the U.S. funded explicit archives within the U.S. NCSA ran one of them for basically 20 years, which is good and bad. Running an archive where you basically get storage if you ask for it means that users often don't really think about what they have. They certainly don't go back and once it's in the archive, clean it up. So there's certainly that when we shut down that archive after 20 years of service, there were a number of users that came in and got their data, and a number of other users that said, I don't know, never mind. So it can be a bit of a challenge, but when NSF kind of got out of the archive business, we still had the tape subsystem in our plans, but we had to kind of recast it a bit. So instead of an archive, we cast it as what we call nearline storage, meaning it's more of a midterm sort of storage. And science teams get allocated time on Blue Waters, both in terms of cycles and in terms of wall time, calendar time, for the period of time that they'll have a project allocated to the system. Basically, the tape storage is allocated along with that calendar time, so they can keep their data on Blue Waters for the life of their project on Blue Waters. But after that time, they need to move that data somewhere else. We do have some grace period that can extend it for a bit, but the key bit here is that we're not providing long-term storage for those science teams. And that's true of the other NSF centers as well, that we've been tasked with not providing long-term storage. NSF specifically doesn't want to be the ones responsible for maintaining that long-term storage. That has given risen to a few other efforts within the U.S. and actually internationally as well. One of which that the NCSA is pretty heavily involved in is called the National Data Service, where we're trying to make a number of tools that provide interfaces to work with that data. So one of the problems with just providing an archive is people just chuck the data in and you can't really do anything with it there, it's just sitting there. What the idea of the National Data Service is to have a more active data store that lets people, other collaborators, and really the general public is too broad, but other science teams make use of that data as if it's a public or a resource that goes along with the publications that came out of that research. And that's one of the knocks sometimes on computational science is that a lot of this sort of data that gets generated doesn't get shared with the community like you would in a publication in some other science areas, which affects the reproducibility of the science and the long-term viability of those results. So the idea here is that if you've got an important set of data set that goes along with publications, that you somehow make that available in long-term storage, but also have interfaces into it that let people do things with it, whether that's just grab pieces of it or whether it's do some small scale analysis on it, that sort of thing. That effort isn't to the point where I think it's deployable today, but there are a number of tools that people are working on to move it to down that line. Again, I'm not going to do slides specifically on that particular software. It's not something I'm intimately involved with today, but it is a project that's going on within NCSA and other institutions in the U.S. I think it's also this Art Research Data Alliance, an international project where they're trying to have similar goals of providing interfaces and longer-term strategies for storage. The actual storage itself is one of those things, at least in the U.S., where NSF has actually pushed it down more to the institutional level. The institutions say, well, I don't have any money to fund this, but it's still a problem. And a lot of the computational science, as well as other science, institutions are supposed to maintain the data for some number of years after the project is actually complete, which puts a burden onto the institutions to figure out how to do that. And even an institution as large as the University of Illinois, that's still a task that they're trying to come to grips with. How do they fund that sort of long-term storage for projects when probably the most likely scenario is you get to the end of a funded project, you have no money left. So who's going to pay for that long-term storage? And it's also true that a lot of grants don't allow you to pay forward. You can only pay as you go kind of thing. So once the grant ends, or even before the grant ends, you can't prepay for storage that's going to have a lifetime beyond the actual funding time period of the grant. So that's a catch-22. You're supposed to have this data on for a certain number of years, but your grant doesn't live that long. How do you pay for it? So those are all problems with this sort of field or area that I don't have the answer to. It's one that a lot of different people are thinking about, trying to figure out how we're going to respond to it in the long term.
What about long-term storage problems? Things get split and things like that. You have to take care of that side as well.
Well, now I guess that's closer to this group actually, long-term flips. So certainly there's a lot of different ways you can do long-term storage. What we're doing on our tape subsystem, I didn't talk about it specifically, but our tape subsystem is, back up. Our tape subsystem is a large, actually 4 spectrologic libraries, 50 movers, 266 tape drives. And we use the IBM, the consortium HPSS software to manage it. So one of the things we did for Blue Waters, well, actually, I should back up. Before Blue Waters, like I mentioned, we had a tape archive for the last 20 years. The way we took care of that particular problem was we dual copied everything. So we kept two tape copies of everything. That's fairly effective. It protects against a single tape failure. It protects against robots.
You know which one is the wrong one.
Yeah.
It's the technology problem. If you need to restore something from the old text, don't have even the text to do that.
Their solution to do that, the technology problem, was to make sure that they put the 2 copies, but they also move stuff forward. So you couldn't leave, you couldn't get more than 2 generations ahead.
Find them, yeah.
Of,
Give them to the other
your
people.
tape. So part of that was, and it's becoming less true. It used to be true that 2 generations meant such a big leap in storage that you didn't care too much about the old tapes. It's just that it took forever to read them all in, so you could write them all back out and repack them. So right, and that's a bit of a problem. So we used to dual copy everything. So you could lose a tape, the robot could smash a tape, you could drop it, whatever. You'd generally be okay. NCSA in general, I think, in the 20 years they ran the archive, they never had an actual full data loss. They were able to always read somehow the data. What we did for Blue Waters, because dual copying 200 petabytes gets expensive, we opted instead to write what's a RAID for tapes, or RAID. And as the name implies, it's very similar to RAID on disk. There's a number of different levels, like the lowest was like 2+1. Just if you have a parity strike, similar to a RAID set, just across multiple tape drives. And that gives us a little bit of a boost in performance because you get won't take drive active on transfer. But it also gives you a protection against the tape failure without having to do a full dual copy. So it reduces the overhead of the redundancy. That's certainly a possibility as well. I don't know that we've specifically looked into that. If you're doing something like, so we've talked so far about tape. Of course, the alternatives might be something more like an object store or something like that, where you are doing erasure coding, or typical object store is 3 copies. You could have multiple copies that are geographically distributed as well. It all depends on how much you love your data, that's right. So I mean, those are good questions. It does depend on how much money you can afford to put into it. Some groups, of course, when they talk about tape, it means they have a tape drive sitting on a shelf over there, and they write their data to tape, and then they stick it in the closet, right? So,
We use the same tape.
Or they might use the same tape over and over again. Or they should write it to a disk drive, put the disk drive in the closet. There are multiple different ways. We certainly have had customers, science teams come to us. We offered a service for doing long-term storage, and they didn't like the cost. They said, well, this is, I would go down to Best Buy or to your local electronics shop, Best Buy, probably a great American thing. I can buy this USB drive for $100, it's 4 terabytes, and you're telling me it's going to be $100 per terabyte to store this. And well, yeah, we actually have people we have to support too. It's not just putting it on the drive and sticking it in the closet. We're trying to make sure your data actually survives. So we have this problem of cheapskates that are want to compare it with the free USB drives that get at conferences versus, so we're trying to build RAID sets or something like that, so we actually have some redundancy and that sort of thing. So you have that tension as well of people always wanting it for free. Obviously, you can't provide it for free. If it's going to be properly supported and properly maintained, there's going to be a cost associated with it.
It's kind of great storage as well.
Yeah.
It's always be more expensive than USB drive and whatever consumer.
Right, absolutely. And at some point, you just have to tell them, if that's what you want, go do it. But I'm not going to do it because you're going to come, if I lose it, you're going to yell at me. So if you do it that way and you lose it, don't come to me. You're the one that screwed it up. So anyway, so file systems. So I'm not going to talk a lot about file systems. It is currently one of the biggest pieces of your data management strategy, of course. I think we talked yesterday, and a lot of people here are running some sort of parallel file system, usually either Spectrum Scale or Lustre, or some BGFS as well. They do continue to evolve. I mean, we've seen a lot of improvements in Lustre in the time we've had it running on Blue Waters. It continues to add new features. The tiered storage is something that's made possible through hierarchical storage management functions that were added to Lustre 2.5. We've found some bugs in that, not too surprising, being one of the first big sites to make use of it. But they are in there. GPFS added similar HSM features a few years ago. We actually originally were planning to run a large system that had GPFS as the file system and HPSS as the back end. So even in 2012, we were working with IBM on HSM features that go into GPFS. So those have been in there a while, but again, I don't know a whole lot of places that have actually tried to make use of them. But each of those file systems is making big improvements. Of course, the newer file systems, BGFS, CaSToRC, and others like that, are probably improving at a faster rate in some ways because they're younger, they have fewer features to begin with. And they will continue to have different features that may make some interesting sense for different folks. The GPFS and Lustre are almost certainly will be the ones that continue to hold the market for the very large scale sites, lots of parallelization, lots of scalability. On the other hand, those sorts of file systems tend to be somewhat fragile. as many of us know. So when we have problems on the parallel file system, it tends to halt everything on the system. We certainly have that issue. A lot of our system-wide outages are related to file systems, so one variety or another. Even when we don't turn the system on, it pauses. We have failovers of servers, that sort of thing, and that pauses. For example, metadata server failover in Blue Waters will pause the I/O from anywhere from 5 to 10 or 15 minutes while it does that failover recovery in the metadata server. Nothing gets lost, but user jobs pause during that time period, which isn't ideal. Users do tend to notice that sort of thing. GPFS probably will continue to lead in terms of overall features because they are a commercial package. They have a lot more enterprise type of features. The challenge with something like GPFS though is what's driving their development. And certainly in the past couple of years anyway, what's driving their development has really not been the HPC space. They've been more than commercial space. They want to sell this product and have a lot of different features that speak to the commercial customer. And that doesn't necessarily lead to a lot of new HPC sorts of efforts or new scaling. And one of the problems that we have with GPFS is its scaling. It's fairly scalable to mid-scale, but I think currently the largest system out there is around 10,000 nodes or so, which is not quite big enough for what we're doing today anyway, but who knows, it might be for tomorrow. But other systems, of course, have different capabilities. If you start looking at systems like object stores, have different features than what we're used to in a parallel file system. And some of those features actually are quite nice. So for those that haven't really used an object store, the interfaces to it are often completely different than what we're used to in a POSIX file system. Although some do, like Ceph, offer a POSIX file system sort of interface as well. But one of the main benefits of an object store is because they're doing multiple copies within the environment, they can have entire servers offline and still have full access to the data. So you can do rolling server upgrades without any direct impact to user data availability, which is quite different than what you can imagine today with GPFS or Lustre. When all of us like to be able to take an entire piece of our file system offline and not impact anything that's running. Typically that means we're down when any part of it's down. So these are so tightly coupled that we have issues whenever something happens. Object stores offer some ways around that, but it added cost to users. We're also looking and discussing with a number of vendors. Probably won't be exactly in our early next system sort of time frame around 2020, but maybe by the mid 2020s, have non-POSIX based interfaces that might hook into things like MPIO or HDF, where they can sit on top of what's a file system, but not necessarily a full POSIX compliant file system. So they can do more relaxed POSIX semantics, which can allow some significant performance benefits. So if you don't have to, if you know, for example, that your parallel access to the file is always discrete, you're never overlapping, and that sort of thing. Some of the locks that have to go in a traditional POSIX compliant file system can be relaxed and removed and allow much greater performance. So those are the sorts of things that we have to be careful about, and hopefully we'll start seeing over the next few years to allow better parallelization on many of these things. One of the other things that I think is going to be the most disruptive in terms of file systems, maybe anyway, is how solid state storage gets used. Many of you have mentioned also that maybe you're using a little bit of solid state today, but I think next generation systems is going to use it much more heavily. Some of it may be incorporated directly into your traditional file system, maybe from DDN or others, where they put a cache layer, basically a transparent cache layer. That's maybe the most discrete, but there are a number of technologies that are coming along that offer flash in other areas that are maybe not transparent file caches. For example, today PRACE sells what they call data warp, which basically are SSDs that fit within their service nodes directly into their compute fabric. The initial way that NERSC, for example, is making use of those is actually as discrete allocable storage. And so you can request for your job X amount of data workspace, and then you create basically data storage on there, maybe even a file system, and stage data out of the primary spinning disk file system into that, and run your job directly against basically flash that's on your compute fabric. providing a big boost in performance. It does require explicit user interaction, but it means that users can have direct control over making sure their data is where they want it to be. That's always a bit of a challenge whenever you talk about file caches, and transparent file caches, to me, always raises a little bit of a red flag. And then I know, for example, the Linux transparent file cache, if you're doing sequential I/O, it never really does the right thing, right? Once you exceed the amount of memory that you have in the file cache, basically you lose any benefit of the file cache, because it's always caching the most recently used stuff. If you're doing sequential I/O, you're always flushing out basically to disk, and by the time you get around to reading it again, there's nothing left in the cache that you're going to read again. So there's a lot of issues with that sort of thing. So if you can control that more discreetly, that might be useful. There are other technologies that, for example, the Aurora system, which is a Intel Xeon 5, will be a Knights Hill, actually maybe Knights Hill Plus based system. They will have HBM memory, and then they will have some amount of the DIMM-based flash memory on each of their nodes, and that memory will be. It's a little unclear even to me how that memory would directly be used, but one of them is a local, basically local file system or local file cache on that sort of system. So we'll allow them to do some things there. That again complicates things a little bit for the user. What goes into that space and what comes out. They have to manage that to some extent to clear that out for each user and each job. But it'll be interesting to see how they make use of that. I think that's one of the things we're going to start to see is it will be possible again to have some local flash on each compute node going forward that you then have to manage either a scratch or whether it's a file cache. In some cases, for those sorts of DIMM-based technologies, you could even use it as extended memory, directly mapped and addressable memory. Which one of those methods of use will win out? Don't know. We'll have to see over the next few years as it comes around.
What about one memory address?
That's essentially what the data work is exactly that. So I think that it is vendor specific, but I think there will be a number of vendors that offer that sort of technology, and it may be very attractive for some uses. It's going to depend on the science team. Some will make the effort to make direct use of that sort of thing. Others want something that's more transparent. It's going to depend on the science team, I think, as to how best to use that, and the tools that's brought on to make use of it. So I think the next few years, we're going to have a lot of shakeout in this sort of thing to figure out how we're going to make use of those technologies. As I think some mentioned, we're gaining, if you look at the traditional memory hierarchy, we could be gaining multiple levels in the storage hierarchy. Flash on system, on node, could be flash on fabric, could be flash in the file system. So there could be a couple of different additions to that layering scheme that, or tiering scheme that could either complicate or simplify our lives. Most likely it's going to complicate that. So they usually do, I guess, right? So I think those are going to be interesting new areas. As I already started to mention, storage tiers. As we're gaining these sorts of things, I think one of the kind of midterm sort of goals will be getting solid-state storage or flash storage to be cheap enough that we can consider using it as a primary file system. So today we can't really do that. Most of us would consider it too expensive per byte to be able to spec out anything that's big enough to be a primary high-speed scratch, for example. But probably within 5 years that won't be true. I don't know exactly where in that 5-year timeline, but somewhat along the way to spec out at least a reasonable sized primary file system out of scratch, out of flash. And that will maybe mitigate some of those complications that we talked about earlier, but most likely that high-speed flash-based storage will be fast, but not large. So most likely that will mean we still want to have another storage tier, just like we have Blue Water, we have disk and tape. Only here we'll probably have something that's even more different between the speed and size of the primary and the speed and size of the secondary. And in that case, the secondary might again use the HSM features that we're trying to work on today for Blue Waters to migrate data out automatically. But back end, instead of being tape, might just be an object store or something else like that. If the users don't have to directly access that back end, you don't necessarily care whether it's an object store or file system or whatever. So certainly the goal will be to design something that allows the automated data movement without adding additional fault possibilities. So we don't want to have something that makes it even more fault prone and easy to take out from the front end. But I think in the meantime, these HSM strategies, we have a lot of policy-based things that we have to start worrying about. Because getting the user data onto the high-speed storage at the right time for the job is a critical function. And it's not something that anybody's really doing today. So it's going to take probably quite a bit of effort on multiple sites to really start to develop strategies to make that work well. All right. So I'm going to shift gears a bit now. Move into discussion of container technologies. We've talked a little bit about containers already. Certainly in the wider non-HPC space, containers have already become very popular for many uses. They're lighter weight than full VMs. They're actually not a VM per se. They're more like a change room jail, basically. So you're running natively on the processor. You have potentially native access to devices and that sort of thing. So it doesn't isolate your performance from different containers within the same system in the same way that a VM does. So that's a little bit of a downside, but it's much lighter weight. So you do have to be a little bit careful with how you're doing it. It also doesn't, there could also be a little bit of security sort of issues there to one container to another. You're not that guaranteed, but it is basically a change room jail. So you actually use change room jails for other things. So it's pretty secure for the most part. Docker, of course, is the most popular solution in the larger community and has a lot of different support behind it. That's one I'm going to sort of focus on a little bit and a version of it on the PRACE system. So the next few slides here, I have more or less borrowed directly from a presentation that Shane Cannon and Doug Jacobson provided on Shifter. They're out in NERSC in the U.S., one of the large Department of Energy Science facilities. And they did a lot of the work on developing and preparing the Shifter software on their systems at NERSC and now on other PRACE systems as well. So while this Shifter itself is a bit specific to the Cray, it's very analogous to Singularity. And I don't know exactly whether they talk to each other or not, but the Singularity developers and the Shifter developers are within a mile of each other. Between NERSC sits on the hill and LB or LB and Lawrence Berkeley sits down below. So hopefully they talk to each other. Maybe a little bit. But certainly, if you look at where data sets are growing and how machines are developing, these are slides from NERSC that kind of talk about their different areas. I think many of us have similar ones. Certainly, it more or less goes for, maybe with the exception of fusion, this all applies to blue waters as well as it does for the NERSC systems. And what they looked at, these are actual NERSC systems, were the shifting of things from traditional HPC platforms, their Hopper Edison systems, which were Cray XE and XC based systems, basically all CPU based systems, and in combination with some data analysis platforms that they had, their Carter system, Mendel complex, and into their new Cori system, which has two phases of it. Cori phase 1 is an additional x86 system, but adds the data warp software into it, data warp hardware, flash-based memory into it. This is the first large system that used the data warp acceleration boxes within it, and a number of people have been very happy with that sort of thing. I don't actually know the numbers off the top of my head in terms of the scale, but it's fairly substantial. And then they added to that just recently, or I guess not now, a few months ago, Cori phase 2, which was a reasonably large Knight's Hill ZM5-based system. So there's two phases, direct interface with the same network. So you've got I believe a Broadwell processor or not, x86 general Xeon processor-based system with flash memory-based storage, and a large Xeon Phi system all mixed together within their compute platform. So within that platform, they have both data analysis capability as well as an additional large-scale compute capability. Is really their goal. And when they look at how things are working, they look at the NVRAM burst buffer, that's the data work capability, and then shifter added on to handle a lot of the different complex workflows that they have. So moving on a little bit. So how many are familiar with Docker? Quite a few. Okay, so I won't say too much about Docker. So Docker, as I said, is the most popular container management software out there. The Docker Hub, of course, is a public repository for Docker images. You can go out there and find probably anything you want. Of course, you got to be a little bit careful about who created those sort of packages. I think the base packages that come from different OSs are fairly safe. I'm not sure you necessarily want to grab any arbitrary package that somebody else may have created, because they can pack it in anything they want, potentially, and some of that may not be something you want. So, but basically, you can build images on top of base images in a very lightweight fashion. So when you package your own app on top of a base image, you only have basically the diff of that image within your additional image, the layers on top of it. And you can share images easily by pushing the Docker Hub, drop them down and run them. You can run them in a wide variety of places. So there's a Docker for Mac OS, for example. You can drop down, you can run your containers on the Mac OS, on the Docker Hub there. It basically it is a very lightweight way to move this sort of stuff around and have basically native OS-like performance out of these container solutions. And also include all the different pieces of software. So instead of having to tell somebody a recipe to build software from scratch, you instead just give them a container. It's pre-built. You run it. It's got all the software. I know it's got all the software you need for it, and it makes it much easier to give people, at least for casual use, a good way to use the software. Use lots of pieces of software without having a burden of a lot of setup. So. So there's some problems to running Docker directly on an HPC system. So we've talked about it a little bit already, but certainly Docker assumes local disk. That's not often the case in our HPC systems. But more importantly, Docker more or less assumes or requires root daemons. And once within the image, Docker assumes that you basically get root within that image. That's all right, I suppose, even in an HPC system. We're providing access to these shared resources. But we also would generally, in an HPC system, would want to make the underlying shared file system available within the image, or else there's only so much you can do if you don't have your shared data available within your compute platform. Obviously, as soon as you provide a shared file system access within an image, giving the user root is no longer viable. So that you have to somehow sparse that out of it. There are other reasons, of course, that Docker is a little picky about its kernel. It requires a very modern kernel. And certainly if you're running a PRACE system, and many of you would have a similar problem than even non-PRACE systems, we have very old kernels. Our Blue Water is a SLUS 11 Service Pack 3, so we're quite crusty at this point compared to what modern, our latest OSs run. And so we have to be careful what we're adding there. And we need to play nice with the batch system as well. We don't want to run the Docker daemon or whatever all the time, all the compute nodes if we're not running anything other than an image. So you can set it up and tear it down and get combination with the image or with the batch system. And in fact, like the user to specify the image they want to run within a compute job as well. So that all needs to be kind of transparent. So the solution that the guys at NERSC came up with, this is Shane Cannon again, Doug Jacobson, they partnered with Cray to design a solution that would run on the Cray platform. Really, HPC platforms in general. I don't know how much is actually, a lot of what the shifter does is really packaged right now for the Cray, but most of what they do, I think, could be run elsewhere. It's not particularly Cray specific. It doesn't rely on Cray hardware or software as far as I know particularly. It's just that currently that's what they've got, that's what we've got, that's all we've really tested it on. So, but the idea here is that you can grab the images, you can run the images with no administrator involvement. That's a good thing for us, right? allows shared resources to be used within the images. So your parallel file system and your they have DBS, which is a PRACE specific sort of thing for getting GBFS within the CRAE available. So basically, it means your shared file systems are available within the images. Because it's leveraging Docker images directly, they leverage Docker Hub directly. So you pull in images from the shared repository and let you push their images there and pull them down. Although they can also use private repos as well. And it provides hopefully a very secure implementation. I will note when we first started testing Shifter, our security team did find some specific security problems with Shifter. We reported them and got both nurses and created to solve them before we went to production with Shifter ourselves. So you do have to be careful with them, but basic components on the Shifter side are an image gateway, and so while it makes use of Docker images, it does squash them down, so it doesn't use the Docker image directly. It pulls them down from the image gateway and then massages them. Basically, while Docker uses layered file systems, layered images, Shifter does not. It has just a single image that you're mounting, so it has to squash this into a single image. The Shifter runtime actually runs as needed on the compute images to launch and set up the images, and then integrate with the workload manager. At Nurse, they're now running with Slurm. We run with Torque Moab on our system. So we look a little bit about the Shifter architecture. Basically, on a login node, in order to pull down the image, the user does a Shifter image pull, and it pulls it into the image gateway node, which prepares the image and sticks it onto the shared file system where it can be found on the compute nodes. Once it's there, the user can then interact with that or submit a request via a QSub or an SBatch command, and that works with the workload integration, which is basically in the prologue and epilogue, and sets up the image on the node, starts the right daemons to get it running, mounts everything up. There's the mounts of the shared file system or bind mounts those into the image as well. So those all show up on the image when the user runs it. Depending on what the user is doing on the CRAE, once they have this set up, they can do an app run, which is the CRAE, the equivalent of API run, and it launches with the app within that image. Alternatively, users can actually do interactive access to those images, and if you do, if we show a little bit, if you wanted to do something that gives you Ubuntu on top of our SLAS, if you do a uname, you get the Ubuntu. It looks just like an Ubuntu Linux distribution, which provides a lot of benefits for using packaging software that they normally run on their workstation in their office, sort of thing. So basically, this is sort of their design for the image gateway. So this is a little bit unique to Shifter, but basically pulls images in directly from Docker Hub. I think that they decided to do that because it was simpler. They didn't want to provide their own image server. They wanted to leverage Docker Hub and basically stores image metadata on there and does the actual image manipulation kind of in the background here. So it's a fairly straightforward sort of thing. This is actually for Slurm. We don't make this quite the same way. There's a custom plugin they did for Slurm to help manage this sort of stuff. So one of the pieces I think was mentioned in the Singularity talk as well. They can also do MPI integration, so that you're making use of the native MPI libraries within the image. In order to do that, you do have to create basically a shared mount. So you basically pull the actual MPI libraries into a shared mount and mount them within the image so they're available within the image. That takes a little bit of effort because those shared libraries aren't necessarily the same on every system, so a little bit of administrative effort to set those up in the right place so you can bind mount them in and make them available. Once you do that, then you essentially can run these applications, and particularly with this phrase an MPI-CH-based API, you can bind, even if they didn't build against those libraries, it doesn't matter because you can overlay the libd MPI-CH shared object in the right path, and even as long as they built against an MPI-CH within their original image, you can basically make use of that shared object to link them to the native libraries of the Cray and let applications that were not even built against Cray specific in GICH to run using the native interfaces. So provides some interesting capability there. That particular part we haven't actually done, but we've done more single stuff. So.
You said that you're using a custom Slurm plugin.
Well, that is available. We don't use Slurm ourselves, so they're using it at NERSC.
Okay, it's something that is public.
Yeah, I believe so. Yeah, everything that within Shifter is actually available on GitHub. So it's an open source project.
Oh.
We have to end the address for this.
So again, mostly they're targeting the Cray because that's what they've got. I don't know how much effort it would take to get Shifter running on a non-Cray platform, but Singularity is likely very similar. I'm talking about Shifter because I know Shifter, so we're using Shifter.
So essentially both Shifter and Singularity are licensing.
They are. They're doing it a little bit different ways, but they're doing basically the same thing. They're trying to get a container technology available on HPC platform and do so in a way that provides the capabilities of the HPC platform while at the same time making sure you're not relaxing security or providing ways for getting around security in your platform.
The kernel is probably quite out.
Yep.
Doesn't cause any problems.
Well, with Shifter, it doesn't. They've gotten around the kernel requirements of Docker. So we're able to run the Shifter latest Ubuntu on top of our, I don't know what the kernel is in SLUS 11, so whatever it is. But it's an old one, right? It's certainly, that was part of the reason for Shifter was to try to get around that. I'm not sure exactly what all Docker does that requires such a new kernel, but they were getting around it, basically.
Just to get off of work.
Yeah, right.
Minimum.
Right. All right, well, let me continue on. So this is just some examples here. So this is actually an example of creating the image. So if you're familiar with Docker, he's basically set up a Docker config to create this application, build the image, and then push the image out to Docker Hub. On the Shifter side, that was independent of Shifter. This Shifter image side, then you go on to a login node basically, and pull the image from Docker Hub, and then this is the batch script that would run it. It's very much like a traditional batch script. This is all basically the same. The only thing that really changes here is that there's this extra directive about the image here in there, and I guess there's a little bit of Mokesh size there too, which I think is more. This is optional. Mostly it's just a matter of specifying the image that you're going to want to run there, and then he runs his application. This is a Slurm batch command, srun, and it runs basically knows it's Shifter and then runs the application within the Shifter image, rather than running something that's directly out of the Lustre file system. What are the benefits? So we talked a little bit before about the benefits here. One of them is simply because you're packaging up your application within a single image, you avoid some of the issues with parallel file systems. And as we all know, metadata is one of the Achilles heels of a parallel file system, particularly Lustre. Because Lustre today really only has a single metadata server, no matter how big your file system is. And so what that image does is you're basically using Lustre as block storage. Lustre is really good at block storage. It parallelizes block I/O really well across the servers. And so when you pull in this image, the local OS caches the inode table. And so your metadata on that image file system is all locally within the image. So you don't have to touch the underlying Lustre parallel file system to mess around with the image itself. So in terms of metadata. So what that means is that things that like to hit have a lot of little file access or that sort of thing can get accelerated quite a lot when they're encapsulated within an image. And so in this case, they're looking at Python startup. So Python, of course, as many of you know, has a gazillion libraries that it pulls in when you typical Python application. And when you have Python all stored on a Lustre file system, there's a lot of metadata that gets involved with that, and it can make the startup kind of slow. So, so they're looking here at different methods of storing Python and where the Python starts up from. And here we can see Shifter is right in the neighborhood of running directly out of TempFS, which is within memory of the node. So really a very impressive improvement in the startup. This is out of 40, almost 5,000 MPI ranks. This applies to other software as well, though, too, and we'll talk about it in a minute here too. So basically, as I mentioned, you've got all these little libraries within the Python namespace, and it has to construct the namespace and walk through it and load up all those dynamic libraries. So this puts all that metadata into something that's in the memory of the node rather than having it in the file system, and it improves it quite a lot. So just similar, basically reiteration the point here that you're bypassing the Lustre metadata server and only hitting it basically for the actual block data, which Lustre's quite good at passing on in parallel. The other major one, and this is one that we're also seeing on Blue Waters, so one of the major uses of Shifter on Blue Waters right now is a project that's related to the LHC experiment Atlas software. They maintain when they do their runs, they have this large set of reference data that gets targeted as well. The reference data is on the order of a terabyte or two in size, but has millions of files. Sticking that on Lustre is terrible. You've got too many files, too many small files there. So what we started to do there, and they did it at NERSC as well, the actual Shifter image actually can be very large. So that we're talking about a Shifter image that's over a terabyte in size, has all that data in it. But that means all the metadata operations and operate within that. And it improved. Looks like I need to move this down slightly here, but the red line is the Shifter line, which means that they're scaling much better on Shifter than they are when they're running out of any other file system there, because they're able to move that metadata access out of the main file system, and similar on the Waters, it gets it out of the main file system, and means that they're impacting themselves and the parallel file system, and thus other jobs much less than they would be if they were operating as a parallel file system. So the other thing, making further use of this, you can look at the image as a local write cache. This is scaling out in the same similar sorts of ways here. So obviously you can see that the IOPS here scales very well with no count, very cleanly. Cruising quite a lot. So in this particular case, they're seeing 100 times faster performance than they do on Lustre at the same scale. The other thing they're making use of, we haven't actually started anybody using it this way, is taking Shifter images that are built with Spark included. Again, Spark likes to do some local write cache sort of thing. Put that into memory instead, which is what we would do even if we weren't running Shifter, but it keeps those stuff within TempFS or something like that. And then you can make use of Spark very effectively on the parallel file system. Anybody who's tried to Hadoop on a parallel file system knows that Hadoop is terrible. You do not want to run Hadoop on Lustre or HDFS on Lustre. It does not scale at all. But you can run something in Spark, and you get, as long as you keep the file caches onto the local node, you'll end up with a pretty good performance. And this is one way to pull it down. I already talked a little bit about MPI. Basically, you have to.
Just wanted to ask a question about the last slide. When you load the Shifter image on nodes, the file systems are still not local, right? You're still using
you mount. They basically mount in the shared file systems within the image, so that they're visible within the image. So you have access to the shared file systems, but you also have the image itself looks like a local file. It's kind of looks like a local file system, even though it's not, but the metadata for that image is local because it tends to, the inode table will get cached within the local memory.
Yeah, but the actual data that Spark is running on,
The actual data that Spark is running on will not be local, that's right.
and that does not affect your performance?
It may somewhat, but as long as you're talking about block data, Lustre and GPFS are pretty good at serving block data. It's where you start to beat them up with metadata that starts to hurt a lot. So most of the writes or reads are okay. The small stuff, this per node write cache that Shifter used or that Spark uses tends to be the larger problem. So if you can keep that local, that tends to mitigate any performance impacts of not having the other data local.
So you read from the parallel file system, but you write cache on the local disk.
Right.
And how much cache do you use? I mean, how much is it?
Well, keep in mind, this is TempFS, so it's whatever memory you can afford to give up, basically.
Okay.
So that's where it comes from. Because there are on the PRACE systems, there are no local storage per se, at least the ones we're talking about here.
And it still works. I mean,
Yeah.
usually Spark takes a lot of memory because it
can,
loads everything into memory. And then you also need to do a TempFS for all the output. I mean,
Yeah.
do you have enough memory?
Well, one of the things we have in spades is memory. On an individual node on Blue Water, it's 64 gigs. But as long as you're scaling reasonably well, we can just throw nodes at it. That's our approach. We've got 1.6 petabytes of RAM in the total system, so that's a lot of memory. So as long as you scale out, you can make use of really large memory spaces. So that's trying to make use of our assets, right? So that's our approach.
Okay.
All right, so I talked a little bit about MPI. Basically, if you have API compatibility with other libraries that are native, you can basically link those in there. I don't want to spend a lot of time on this. I guess I'm doing all right on time here. So this is a similar sort of thing. He's doing just another example of running MPI, the same sort of thing. Same sort of application pull. He runs, this is using salloc instead of srun, but same sort of thing. Runs in the same sort of way, and it just automatically binds to the ABI of the MPI library. So, from the user point of view, this is sort of interesting. We've got 4 or 5 teams of Blue Waters today that are making use of it, all for similar reasons. Basically, the reasons typically are they're developing their software on other platforms, often that are we have a more recent OS than what Blue Waters happens to have. So this allows them to encapsulate that OS dependencies in a way that they don't have to worry about it when they move from one system to another, and lets them run as they had before. It also has some advantages in terms of mitigating some metadata performance issues for application data and science data potentially. So that's very good. Looking forward, to the issues with OS compatibility are something that we're very keenly aware of on Blue Waters. As I mentioned, I think yesterday, we're end of life with the software running on Blue Waters essentially. So we're SLUS 11 Service Pack 3, and that's all we're going to get. PRACE is not planning to do any more major updates for our platform. That means that in 2019, as we're ending operations, we're still SLUS 11 Service Pack 3. So it's going to be a pretty old OS by that point in time. Users can get kind of grumpy about that. They don't want to have to build their software against ancient versions of Make and compilers and runtime sort of libraries. So this is a way that they can move applications they've developed, perhaps with too much dependency on newer software. I might argue that point, but let them move those applications directly over without having to do major efforts to port them to an old system. So run within the image, they see all the software they're expecting, and definitely improves reliability and portability of the software. And it can also improve our reproducibility. So because you're encapsulating the entire set of software, they're more immune to changes in the underlying software stack. So That's a good thing in general. It's still not a full VM, so there, it's not quite the same as being able to encapsulate a full VM and isolate changes in the kernel or underlying drivers. But it goes a long way to removing dependencies on the standard CLib or something like that might have some change in performance between the version they originally built with and the version you happen to have on your OS right now. So it does reduce variability from that point of view. All right, so.
One of the concerns that we sort of have with a lot of new containers on our customers is that you mentioned that the obvious performance improvements that you get by everything together and connect anymore, but they have a huge compiling the software. And probably when you take the easy way out and just use whatever GCC is in the OS and compile to the gap and compiling it, for example, Intel or PGI or whichever expenses compiling you have. Is that a concern as well?
To be honest with you, we don't think we'll see the highly parallel applications making use of these container technologies. Mostly where we're seeing today, the waters of all we're seeing today are the guys that are doing lots of individual single node runs. They're often running things like Python apps and other things like that that are, let's say, not worried about performance to begin with. So we haven't worried so much about that. You're certainly right. In general, if they're compiling within a shifter or within a Docker image, they're compiling on whatever hardware they have to be compiling on. And so at the very least, they're certainly not optimizing for the hardware that you have. So there's certainly a large truth to that. But I think from what we're seeing for the most part, the types of runs, types of uses we're getting are not the ones that are super performance critical. It's more expedient to get them on and let them run than it is to worry about the last ounce of performance in that case. So if they're worried about performance, they wouldn't be running Python, right? So,
They're not worried about performance, what are they going to do?
Well, the optimal performance is not always the key bit, right? I mean, there are reasons that people run there that it's just a matter of scaling and accessing compute resources. So the platform, the ones that are running on there today are mostly, projects related to actual experiments. So I mentioned LHC. We actually have 2 LHC related projects that are running on there doing data analysis from LHC. We also have a project that's running data from LIGO and a couple of telescope projects. So they're doing more or less image analysis based on there. But it's just a matter of where can they find the compute time to do the large amount of work that they have to do. Would I like them to do more optimization of their code and for the system? Sure. But at some point, getting them up and running is more important than worrying about the last ounce of performance.
You can't run it.
Yeah. You're 95% along and getting them from 0 to running, and that's more important than the last 5% for performance, unfortunately. We have enough trouble getting the highly parallel applications to do optimization. The other guys like this. So. All right, so I'll jump in a little bit to deep learning. We don't have a lot of deep learning or machine learning sort of software running on Blue Waters today. I mentioned our crazy Python support guy who supports everything. So he easily just rolled in TensorFlow and Cafe and everything within his packaging. And we're providing that to a few teams. Many of the teams that we're seeing today are not well developed in terms of the machine learning sort of usage. They're often experimenting with it. So having it run optimally is not too terribly important, and the amount of usage is very low. But we are getting some packages, some teams that are finding some uses for it and may move into production in the near future. One of the problems we do have is even though our Python guy is able to get these built and packaged up, our support of them is lagging. We don't have the personnel that know how to use them to make them use. This is something we're working on. Actually, we have a couple guys we're trying to hire right now that hopefully will enable have some background in this software to have better support. So that's been a challenge for us over the past year or so in deploying this sort of software out there. So So this is sort of a kind of a little listing of Blue Waters. So we don't have our number of projects is relatively modest. We have a couple hundred projects total. So having this number of projects that are making use of some sort of machine learning actually is reasonably impressive out there. So a lot of these are small scale sorts of things. Actually, most all of these are small scale sorts of things. Actually, they're small projects compared to the big typical projects on Blue Waters. They're really looking at it as an experiment in most cases. So, but they're pioneering the use there. So as they get some experience with it, we're getting some experience with it. We'll see it more. And I'm sure as we look forward to the future systems, we're going to have to support this as a first-class set of software. We're going to be expected by users to support it. Big data. I'm not going to talk a lot about big data as well. The big data ecosystem you're talking about here is typically the Hadoop ecosystem. There's a lot to this sort of thing, and if you had to support it for users, how many support Hadoop on some sort of platform within their center today? Just a couple. Supporting it is similar. Well, it's even more complex than the deep learning sort of software in that you have a whole nother set of software, a whole nother terminology that has its own batch system, so to speak, in the yarn sort of stuff, own database. It's a whole new terminology sort of area. So it's a little complex to support. There are many that are out there. Typically, the ones that I think most people use are Hadoop or the Hortonworks sort of distributions. They provide some nice tools that allow you to set them up very easily. I'm not really going to skip through these a little bit quickly here, but just some basic background material on Hadoop. Hadoop, first of all, most of these tools are written in Java, or at least the Hadoop itself is written in Java, which immediately tells me it's not very high performance. But I'm not sure that I want it on the HPC system, but there are some advantages there. It does scale very well because they're replicating data. You're basically sending the problem out to where the data is on the node there. And it provides a very simple API. And that API scales very well. So this is another point. We talked about developer tools yesterday. This is another point that we get with people that are just learning to code and learning to parallelize. They compare doing something like MapReduce, which is very, very easy to write a program that parallelizes very well across the system and does something useful, we can argue, and can handle large amounts of data, to having to write an API program or a threaded program, which is much harder for users to be educated on and grasp. So to give an example of how some of these new technologies, while they aren't as necessarily high performance as the older ones, are so much easier to use that the students that are learning them obviously want to use them. They want to use them instead of having to figure out how the heck to write an API program that you have to explicitly pass messages around. Who does that anymore, right? So that can be a challenge. You can run Spark on HDFS. That's what if you run the Hortonworks distribution or Barry distributions, that's what you would do. We on HPC platforms typically don't want to do that if we're sharing hardware. And that's what I'm going to talk about a little bit here. Blue Waters, that's what we want to do. We want to run Spark, or we want to run Spark directly on Lustre or directly on 10FS or something like that. We do not want to run HDFS on top of there. It doesn't run well. Hadoop itself does not have that option. You don't want to run HDFS, basically. The advantage of Hadoop when you do run HDFS is that they were designed for inexpensive nodes, lots of inexpensive nodes, cheap storage, that sort of thing. Very, very simply parallel. You don't need a real good interconnect for that sort of thing. That's great on a cluster if it's by itself. And that typically, I think, if you're running Hadoop today, you're probably supporting it in that fashion. Run it on a separate set of hardware. Don't try to share it with your regular HPC platform. Spark, on the other hand, you can get running on the HPC platform relatively effectively. I'm not going to run through this, I'm running out of time here.
There are ways of running just Hadoop clusters in Java.
Yep. You can do that. We're typically not today at NCSA. Let me skip through a couple of these. The definitions here are different components. As I mentioned, there are a lot of different components within a typical one that maybe your users need some and maybe not. Most of them really don't need that. Spark is where if users come to you and say, well, should I learn Hadoop or should I learn Spark? Point them at Spark. Spark is the more recent one. It's much more scalable. It's much more amenable to a typical HPC platform than is Hadoop. So that one I'll say for sure. It leverages memory much better than Hadoop does, and can scale much better for certain types of operations at least. If you're deploying an independent platform, Bar is a nice way to go. Provides a nice packaging that lets you easily deploy a system on a set of nodes. On Blue Waters, we're currently messing around with Spark. We want to avoid, as I mentioned before, HDFS, utilize the large memory capacity of the system. We have another NCSA system that I guess I didn't put a full description up here. That's a small scale system with only 16 compute nodes, but it has a large data file set, so it's got 5 petabytes of storage managed by GPFS. There they divided up those 60 compute nodes in a hard way, so they've got a section of them that are dedicated to running Hadoop sort of jobs running HDFS, and a set that will run traditional HPC applications, and another set that run OpenStack applications. Those don't move back and forth. They're 3 independent, 3 side-by-side sets of nodes, essentially, separately managed. And in particular, the Hadoop section, there they are running on top of GPFS using what's called a Hadoop connector GPFS. That seems to run fairly well for them. I have not seen anything similar to that works well on Mustard. On GPFS, they're running, I will mention that all of them running on GPFS, they're segmented off a separate GPFS file system for the purpose of the Hadoop work. They're not running off the home file system per se, for example.
Sorry, did you say 60 or 16 machines?
60 machines total, divided into 3 groups. I don't remember exactly the numbers of each one, but it's not a very big no count compute-wise, but it's data-rich sort of thing. That's the point of the system. Their particular research area is geospatial information science. So they have a lot of image data sets and large mapping data sets and that sort of thing that they're doing analysis on with these technologies. All right, so wrap up here with some little discussion on virtual machines. So we don't do very much with VMs themselves on Blue Water. We do nothing on the PRACE with VMs. We don't even support VMs there. The only place we use VMs at all is on, we have a VMware cloud outside of Blue Waters that we use for some of our infrastructure servers, LDAP, license servers, and that sort of thing. There's nothing that's directly user accessible. When we look going forward, certainly we can imagine needing to support some sort of VM capability like a small OpenStack sort of capability to provide some persistent services that we've currently not offering directly, but we've had requests for. So, for example, some of the teams would like to have an SQL server or something like that that's persistent to allow them to talk to from their jobs and manage some of their job outputs and that sort of thing. That's something we don't do today. Our view of OpenStack within, well, probably would be the future of Blue Water would be this, the number of these would be fairly small and wouldn't be used primarily for compute, there'd just be some persistent data services. This is actually the Roger system I just mentioned. So I'm talking more about that since I talked about it already. Again, it's a small Dell cluster sort of thing. So, and that system does also do an OpenStack environment. Our experience with OpenStack has been okay. And with the Roger environment, they've upgraded, I think, once. OpenStack does a pretty good job of providing private cloud. Really kind of the goal there. It's open source, and a lot of people are contributing to it. There's a lot of changes that happen between major versions. If you're supporting OpenStack, it is a completely different language, basically, than your traditional HPC. So there's a lot of different things. The people that are developing for it is very rapid development in some areas. So these folks are quite willing to break things from one release of OpenStack to another. So you have to be careful. As I used to say with compilers, they don't necessarily fix bugs, they just move them around. So they do break things from one release to another, making it somewhat challenging to do an upgrade. Upgrades in general are a somewhat foreign concept to them. The way they upgrade is to buy a new set of hardware and install a new set. So they're just getting around to thinking about, oh, maybe somebody would actually like to upgrade a place. So it's not a well-baked thing to do that today. So you have to be careful with that sort of thing. Right now, we originally had the idea that, gee, wouldn't it be great if you could actually make use of the bare metal deployment with an OpenStack to deploy some of your HPC resources. Today, we haven't made that work. There's a lot of challenges in that because, of course, OpenStack wants to manage each set of instances within private networks and deal with a lot of the networking stuff with itself. And it may not be, at least, it's not trivial to figure out how to manage your HPC high-speed network and file systems within that sort of private networking sort of space. So there's particularly if you're dealing with something like GPFS, which is particularly obnoxious about dealing with different subnets and that sort of thing when you're setting it up. So our view is that you have to be careful with this. Today, anyway, we're looking at OpenStack as sort of something you set up on the side. It's not directly integrated with a lot of your HPC resources. And where we are using it, the extent of the integration is basically NFS exporting pieces of your HPC file system into the OpenStack space so that users can mount the data that they would have access to in the HPC file system on their VM to do some data surfing, that sort of thing. Typically that means we export either a home directory or a specific project directory to them. So we don't allow them to view the entire directory space because of course they have administrative access within the VMs. So that would be a no-no. All right, so wrapping up since I'm out of time. Really, data analysis and data services go quite a bit beyond what we originally were talking about only a few years ago. So there's a lot of folks that are going to be expecting some sort of containerization or VMs in future systems. We're going to have to support various new software from Spark to TensorFlow to other sorts of machine learning and big data software that will need to be integrated with an HPC environment. So they're going to have to be supported on our systems moving forward. And they're not trivial necessarily to do that. So there's new things we'll have to learn and new techniques to support those. So since I'm out of time, I'll just put my acknowledgements and certainly acknowledge John Maloney and CSA for some of his slides. Certainly Shane Cannon and Doug Jacobson, since I liberally ripped them off from my presentation on Schedter, as well as our funders.
Those are the developers of
Schedter. Right.
Did you use any single system image options? I mean, combine servers into one big server.
Oh, we do not use anything like that today. I really have very little experience with it myself, actually. Are you using that today?
We tried. There is an Israel company which is called ScaleMP, which is
Right.
which provides us the services. So
I know our industrial program partners, we're talking with them, but I have not heard that they've moved forward with any sort of testing or use case for it.
yes.
Anybody else? All right, well, I think it is time for break. I'm assuming break food's out there. So. All right, thank you.
Yeah. mean, if you break the
Well, actually, that's pretty unfortunate.
you can customize the only issue do is run the module CMD query see if it's actually yes. I recently I've tried moving
It's always the first.
it's a very good reason to speak to them. I know. Support housing you can also do is just maybe it's okay. I don't know how this was packaged.
Yeah, sure. It's not always ideal. Pretty well.
But it's a program.
Modest scale, you're probably okay. Mostly, you have a little bit.
It's possible you never see this problem. Just creates that.
How do you get the
Probably the language environment.
bigger issues? Your TFA.
That's very weird. People that copy paste commands and yet.
Yeah,
There's
that's
like
true.
a dash I've stared at that stuff for hours. Why is this? What do you mean the option doesn't exist?
Don't even see the character, special character, but you know it's hidden character.
Tired? So you're no, tomorrow, around noon. I didn't want to rush out. So if you have any oh, tomorrow I'll just sleep in flying out around noon, so we don't have much stuff. Oh, no, yeah. Sure. Yeah. Excellent. It's not there. Yeah. Okay. So let's see. Did you change the visible configuration? No. Okay. So it's in the context of the configuration. So it's also a room directly, not locally visible. So these two. Yeah. You'll get a software directory, local directory, download resources there. This is build directory, which should be available. Info build directories are and then this unique files and code, this is a copy of these translate for artifacts. So the modules are installed in modules. This is where all the modules are, and these are simulated. We have to wire these are symbols together. So what you want to do is you want to add this directly to you want to use this and then you can. The thing is, easy to run it by itself. Those are the control modules, so make sure that applications and that's why it's finding the module and it's good that it worked. It was easy to install Word, right? No, it's easy. Yeah. Some step to install it. The only problem is that